For years, one faint ghost-like object in our own galactic neighbourhood has confused astronomers. Geminga, a neutron star that blazes in gamma rays while staying almost completely silent in radio. It breaks the usual rules of how these stellar remnants are supposed to shine challenging, long-held ideas about pulsars and their magnetic fields. Today we explore why this strange neutron star seems like it should not exist at all. If you enjoy cosmic mysteries like this, please subscribe and share, and tell us in the comments, what would you ask about a neutron star that shines in gamma rays but refuses to speak in radio? Thank you for watching. Now let's begin. From a broad view of the Milky Way, Geminga lies within a large flattened system of stars, gas and dark material that forms a rotating disk around a central bulge. The galaxy stretches out as a wide, thin structure with spiral features that wind around the centre, and the Sun orbits within one of these spiral features rather than near the crowded core. In this disk, lanes of interstellar gas and dust run between swaths of stars, and clusters of young stars appear, where gas has recently collapsed and formed new stellar groups. The Sun sits partway out from the centre, in a region that astronomers often describe as a quiet suburb of the galaxy, compared with the bright inner regions, and Geminga occupies a neighbouring part of this same broad disk. Both objects travel around the galactic centre under the pull of the combined mass of stars, gas and unseen matter, so that on very long timescales, the entire neighbourhood slowly sweeps around the core of the Milky Way. When the sky is surveyed at different kinds of light, this familiar star field reveals layers that cannot be seen with ordinary eyes. Maps of radio waves trace cold clouds of gas, maps of infrared light reveal glowing dust and cool stars, and maps of high-energy radiation show a very different pattern again. In the highest energy range, where gamma rays carry far more energy than visible light, the Milky Way appears as a broad band of emission that follows the galactic plane along with scattered points and patches that mark sites where energetic particles and strong fields interact. In the direction of the constellation Gemini, a region that human observers know from visible star charts as a pattern of bright stars on a dark background, these gamma-ray maps reveal one of these points as a steady bright emitter of high-energy radiation. To describe this location, it helps to picture the galactic plane as a thin mid-layer of the disk. The Sun sits close to this mid-layer, only a small distance above or below it on galactic scales, and Geminga lies in roughly the same general ring around the centre, but shifted slightly above the main plane. This small displacement is modest in absolute terms, but is enough that when plotted in galactic coordinates, Geminga does not sit exactly on the ridge of brightest diffuse emission that marks the midplane. Instead, it occupies a position just off that ridge in a part of the sky where the background glow is still present but somewhat less intense. The line of sight from the Sun toward Gemini runs through the local spiral structure, rather than toward the central bulge, so the density of intervening gas and dust is moderate rather than extreme. As a result, high-energy photons from this region can reach detectors in orbit around Earth, with relatively limited obscuration compared with lines of sight that cross thicker parts of the disk. When gamma-ray telescopes scan this direction, they record a combination of diffuse emission from the galactic plane and discrete sources that stand out above that background. Geminga appears in such maps as one of these discrete sources extending over a region that is broader than a single star in visible images but still compact compared with the overall band of galactic emission. Before its nature is established, it is simply one among many high-energy lights, notable for being bright and steady, yet lacking an obvious counterpart in visible or radio surveys. This makes it part of a class of high-energy sources that initially appear anonymous, bright in gamma rays, but not clearly matched to a known type of object at other wavelengths. Early surveys with space-based instruments catalogue such sources and assign them numerical names, filling lists with locations on the sky, where gamma rays arrive more often than from the surrounding regions. In these catalogues, Geminga is recorded first as a position, and a brightness, a set of measurements against a coordinate grid not yet linked to a familiar kind of star or remnant. Over time, repeated observations confirm that the emission from this location persists over many years, rather than flaring and fading like a transient event. The source does not show the rapid changes expected from some explosive phenomena, and instead behaves as a long-lived member of the high-energy sky steady on human timescales, even as it slowly drifts across the background of more distant objects because of its own motion through space. From the standpoint of galactic structure, Geminga and the Sun thus share two important roles. They both participate in the overall rotation of the Milky Way disk, and they both sit within the same general layer of stars and gas that orbits the galactic centre. The Sun provides the vantage point from which the sky is mapped, and Geminga provides one of the bright markers in those maps, marking a location slightly above the midplane and toward Gemini in the outer part of the disk. In absolute distance, Geminga is relatively nearby compared with many sources in the galaxy, lying within a few hundred parsecs, which corresponds to several hundred light-years. On the scale of the Milky Way, this is a short separation, placing Geminga well within the local galactic neighbourhood of the Sun. This proximity helps explain why the source appears comparatively bright in high-energy surveys, even though it remains faint or invisible in ordinary light. It also means that the environment around it, including the surrounding gas and any larger-scale structures, forms part of the same local region that contains the Sun, nearby stars, and the local interstellar medium. Only after many observations and careful analysis does the picture of this source change from an anonymous high-energy point to a specific kind of object. The steady emission, the relative closeness, and the lack of a strong visible counterpart point toward a compact remnant rather than an ordinary star or distant galaxy. Detailed studies eventually show that this source is a neutron star, the dense remnant left behind when a massive star ends its life in a supernova event, and that the gamma rays trace ongoing processes in and around this remnant rather than a brief one-time explosion. From the perspective of galactic structure, Geminga and the Sun occupy the same general spiral environment within the disk of the Milky Way, sharing a neighbourhood often called the local spiral arm or local spur. This region is not a sharply defined object with a hard boundary, but rather a swath of stars, gas and dust that threads between two of the larger, more massive spiral arms, nearer and farther from the galactic centre. Within this swath, clusters of young stars, associations of massive hot stars and more ordinary stars like the Sun, appear together mixed with clouds of interstellar gas that have only partly turned into new stars. The Sun orbits within this local structure at a distance of many thousands of light-years from the galactic centre, following a nearly circular path that keeps it away from the crowded inner bulge, and Geminga also lies within this same broad band offset from the Sun by only a few hundred light-years. Because that separation is small compared with the overall scale of the galaxy, both objects see nearly the same large-scale galactic environment. The same overall gravitational field shapes their motion around the centre. The same pattern of spiral structure passes slowly through their region, over long times, and the same general population of nearby stars and gas clouds extends around them. In maps that trace the positions of nearby bright stars, the local arm appears as a slightly curved arrangement of stellar groups, including well-known constellations as seen from Earth. The familiar pattern of Gemini is part of this structure, not a separate physical object, but a chance alignment of stars that happen to lie in a similar direction in the sky. Some of these stars are relatively close, some much farther away, yet together they outline the shape that human cultures have long recognized. Along this line of sight, catalogues list open clusters of young stars and associations where massive stars were recently born. These groups illuminate the surrounding gas and leave traces in the form of shells, bubbles, and regions where the interstellar medium has been stirred by winds and past supernovae. Geminga resides among these imprints of earlier stellar activity, one compact remnant within a wider stellar population that has already passed through several cycles of star formation and death. The Sun, though older and less massive than the stars that explode, as supernovae also belongs to this evolving environment. Both the Sun and Geminga orbit the galactic centre, with speeds of many hundreds of kilometres per second, but because they share the same general orbital path, their relative motion on galactic scales is modest. Over millions of years they drift with respect to each other as they move through the gravitational field of the Milky Way and through the slowly changing pattern of spiral arms. On shorter timescales, the most relevant motions are those relative to the average flow of matter in their local region, called the local standard of rest. In this frame, stars may move with small but significant peculiar velocities, and Geminga is one of the objects whose own peculiar motion stands out when studied with precise measurements. Surveys of nearby stars in the local spiral arm show a mix of stellar ages and types. There are long-lived low-mass stars that have been present for billions of years, intermediate mass stars like the Sun, and younger massive stars that will end their lives quickly. There are also compact remnants such as white dwarfs and neutron stars, though these are much harder to find because they emit little visible light and can be small and faint. Geminga represents one of these hidden products of earlier star formation. Its presence in the local spiral arm indicates that at some time in the past, a massive star in this neighbourhood exhausted its nuclear fuel, collapsed, and exploded as a supernova, leaving behind a dense core that now moves through the same broader environment as the Sun. In three-dimensional maps of nearby space, the position of Geminga can be described by its distance from the Sun and its height above the galactic plane. Its distance is constrained by parallax measurements and other methods, with estimates placing it at a few hundred parsecs, which corresponds to several hundred light-years. Its height above the midplane is much smaller than this, making it part of the thin stellar disk, rather than the thicker distribution of older stars that extends farther above and below the plane. This placement means that the gas density around it is characteristic of the local disk low compared with dense star-forming clouds, but not as low as in the halo regions far from the plane. When astronomers construct models of star formation in the local arm, they include episodes of clustered starbirth in associations and OB groups, where many massive stars form together. Over time, winds and explosions from these massive stars carve cavities and bubbles in the surrounding gas, and the surviving low-mass stars and remnants continue to orbit within and around these structures. Geminga can be regarded as a witness to such an episode, a remnant that still carries the motion imparted by its birth environment, and by any kick it received when its progenitor exploded. Its current path through the local arm is therefore a combination of the common orbital motion shared with the Sun and a smaller distinct velocity component that causes it to drift relative to nearby stars. From the standpoint of high-energy astronomy, Geminga's location in the local spiral arm is helpful because it reduces the complexity of the line of sight. The region between the Sun and the neutron star contains a relatively modest amount of gas and dust, compared with lines of sight toward the inner galaxy, so absorption of high-energy photons is limited. At the same time, the broader neighbourhood is not empty. It includes low-density gas remnants of old star-forming regions, and diffuse material that can interact with energetic particles emerging from the neutron star. In this way, the local arm environment sets the large-scale conditions in which Geminga evolves and emits high-energy radiation, and it defines the nearby galactic context that surrounds this neutron star and the Sun alike. On scales of a few hundred light-years around the Sun and Geminga, the space between stars is filled with the interstellar medium, a mixture of gas and dust that is extremely tenuous, compared with any atmosphere on a planet. Most of this gas is hydrogen, with smaller amounts of helium and traces of heavier elements, and it appears in different forms depending on temperature and density. There are cold, dense clouds, where hydrogen is mostly neutral, warmer regions where atoms are partly ionized, and hot low-density cavities where gas has been heated and pushed outward by stellar winds and supernova explosions. In the local neighbourhood, both the Sun and Geminga lie in or near such a cavity, often described as a local bubble, where the gas density is low and the temperature is high, compared with denser clouds elsewhere in the galaxy. This region extends over tens to a few hundred light-years and is thought to be the combined product of multiple supernovae and strong winds from massive stars that once formed in nearby associations. As these energetic events blew material away, they left behind a volume in which the remaining gas is thinner and hotter, bounded by shells and arcs of cooler, more neutral gas that mark where outward-moving material has slowed and piled up. Observations of neutral hydrogen at radio wavelengths reveal these shells and arcs as curved features on the sky, and models of the local interstellar medium attempt to reconstruct the history of the explosions and winds that formed them. Within this structured medium, Geminga travels through gas that is already shaped by these past events. Its current position places it in a region where the density of interstellar gas is relatively low, so the mean free path of particles and radiation is large compared with conditions inside dense molecular clouds. This does not mean the space is empty. Rather, it means that the average number of atoms in a given volume is small, and their interactions occur on larger spatial scales. For a neutron star moving at high speed, this environment influences how any outflow it produces interacts with the surrounding medium, how shock fronts form, and how far high-energy particles may travel before scattering. Maps of the local interstellar medium show that the low-density cavity around the Sun is not uniform. It contains sub-regions of slightly different density and temperature, and it may be connected to neighbouring cavities carved by supernovae in nearby clusters. At the boundaries between these regions lie sheets and filaments of cooler neutral gas traced by emission from hydrogen atoms and other species. Some studies suggest that Geminga is associated with or near one such extended structure, possibly linked to an older ring or shell of gas left by one or more supernovae in the local arm. In this picture, the neutron star and the neutral gas structures are different outcomes of related episodes of massive star evolution, the remnant core moving through space, and the pushed-aside interstellar gas now forming an arc or shell. However, the exact connections between specific shells and specific explosions remain uncertain, because many energetic events have occurred in this part of the galaxy over millions of years. Astronomers therefore treat these associations with care, comparing positions, velocities, and ages in order to test whether a particular neutron star and a particular gas structure likely share a common history. In the case of Geminga, its relatively small distance from the Sun and its position with respect to known neutral hydrogen features make it a candidate for such links, but definite statements about a single parent shell or cavity remain the subject of study rather than firm conclusions. Beyond these large-scale shells, the local interstellar medium also contains smaller clouds and filaments. The Sun, for example, currently resides in a small warm cloud embedded in the broader low-density bubble, and there is evidence that the neighbourhood of Geminga includes comparable small-scale structure superimposed on the background cavity. These clouds can have higher densities and lower temperatures than the surrounding hot gas, and they may play a role in shaping how shock waves from old supernovae propagate and fade. As Geminga moves, it may pass through regions of slightly different density, but on the scales relevant for its immediate surroundings, the overall impression remains that of a thin gas compared with denser star-forming complexes. The low-density environment is important not only for the dynamics of gas, but also for the transport of high-energy particles. When energetic electrons and positrons or other cosmic ray particles move through the interstellar medium, their paths are influenced by magnetic fields and by collisions and scattering with gas and radiation. In a thinner medium, they can travel further before losing energy, while still being guided by large-scale magnetic structures that thread the local arm. The details of this transport, including how quickly particles diffuse away from their source and how their energy spectrum evolves, depend on properties of the local gas and fields that are not yet known with high precision. Studies of the region around Geminga use observations of gamma rays produced when these particles interact with the background to infer characteristics of the local medium such as the effective diffusion rate and the magnetic environment. The results suggest that the conditions in the immediate vicinity of the neutron star may differ from the average values assumed for the broader galaxy, with implications for how energetic particles move in this part of the Milky Way. Neutral gas structures around Geminga traced by radio and optical observations provide further context. They show where gas has cooled and recombined after being disturbed, where it now forms sheets and layered structures that can serve as boundaries between different phases of the interstellar medium. These structures may have complex shapes when viewed in 3 dimensions, but on the sky they appear as arcs and loops that encircle or pass near the position of the neutron star. By comparing the velocities of these gas features with models of galactic rotation, and with the inferred motion of Geminga, astronomers can test whether they share a common origin in past massive star activity. Even when such links are not fully established, the presence of these neutral shells confirms that the local interstellar medium is not smooth. It is the record of many energetic processes that have heated, compressed, and rearranged the gas over time. Within this environment, Geminga travels through a low-density volume, shaped by earlier supernovae and stellar winds, surrounded at larger distances by neutral gas layers that mark transitions to denser parts of the local arm. The combination of a nearby neutron star, a structured but thin interstellar medium, and surrounding cavities and shells, sets the stage for the high-energy phenomena that later sections describe in more detail, while the focus here remains on the character of the gas and its large-scale arrangement around the object. In radio and optical surveys of the nearby Milky Way, the gas around the Sun and Geminga does not form a uniform haze, but instead shows arcs, loops, and shell-like structures made of neutral hydrogen and other elements. Neutral hydrogen is hydrogen in which the electron remains bound to the proton, and large collections of such atoms emit and absorb radio waves at a characteristic wavelength that allows astronomers to map their distribution in 3 dimensions. When several massive stars in a region expel strong winds and later explode as supernovae, their combined energy pushes the surrounding gas outward and piles it up into curved layers, leaving a bubble of lower density material inside and a shell of compressed gas at the edge. Over hundreds of thousands to millions of years, these shells expand slow and begin to fragment, but they can still be traced as partial rings or arcs in maps of neutral gas and in faint glowing emission at visible wavelengths. The local bubble that surrounds the Sun is one example of such a structure, and there are neighbouring bubbles and shells that interlock or overlap with it. In the direction of Gemini and surrounding constellations, surveys of neutral hydrogen reveal large-scale arcs that suggest the presence of older expanded shells linked to past episodes of massive star formation. Some of these structures encircle regions of enhanced soft X-ray emission, which is X-ray light of relatively low energy, produced by hot thin gas filling the interior of old supernova remnants or superbubbles. Others coincide with filaments of dust and ionized gas, indicating that shock waves from ancient explosions have swept up and compressed interstellar material. Geminga sits within this complex pattern of cavities and shells. Its present position places it near or within volumes where the gas density is lower than average and near the edges of broader neutral hydrogen features. This placement is consistent with the idea that the neutron star is the remnant of a supernova that occurred a few 100,000 years ago in the local arm, although the precise link between the current position of the star and any single shell on the sky remains uncertain. When a massive star explodes, the outgoing shockwave races into the surrounding medium, while the dense core left behind can receive a kick that imparts a substantial space velocity. Over the time since the explosion, the shockwave slows and merges with the environment, while the compact remnant travels along its own path, so the remnant does not remain at the geometric center of any surviving shell. To reconstruct the history of a particular neutron star, astronomers combine measurements of its distance, its proper motion across the sky, and its estimated age with maps of nearby gas structures. In the case of Geminga, spin-down models which relate its current rotation rate and slow down to an approximate age suggest that it has existed in its present form for several 100,000 years. Its proper motion measured by tracking its changing position against the background indicates a significant transverse velocity. By projecting its path backwards in time, researchers can estimate the region in which the original supernova likely occurred. Some studies point toward an origin in or near an older star-forming group in the local arm, and they examine whether any known neutral hydrogen shell or soft X-ray loop could be the faded remnant of that explosion. One candidate in this context is a wide, faint structure sometimes referred to as a ring or loop in soft X-rays and radio emission, which extends across a broad region of the sky and has characteristics of an old expanded supernova remnant. The angular separation between Geminga and the apparent center of this ring, together with the inferred age and velocity of the neutron star, makes it plausible that the two share a common origin, although the uncertainties remain large. Other possible associations consider different shells or bubbles in the local interstellar medium. Because many supernovae have taken place in the nearby galaxy over several million years, the gas distribution is the result of overlapping events, and it can be difficult to tie one neutron star to one specific shell with high confidence. As a result, discussions of Geminga's parent remnant highlight scenarios and likelihoods rather than single definitive identifications. What is clear is that Geminga moves through an environment that bears the marks of past massive star activity in the form of low-density cavities and extended neutral gas structures. The energy released by earlier generations of massive stars, including the progenitor of Geminga, has heated and evacuated much of the gas in this region, leaving a patchwork of hot, thin interiors bounded by cooler, denser shells. The density of gas that now surrounds the neutron star is therefore set not only by the general conditions of the galactic disk, but also by this particular history of explosions and winds. That density in turn influences how any outflow from the neutron star interacts with the medium as it moves. In directions where the neutron star encounters slightly denser patches, shocks can become stronger and more compressed. In directions where the gas is thinner, outflowing particles can travel further before being slowed. The neutral shells and cavities around Geminga also affect the larger scale distribution of magnetic fields in its neighborhood. Magnetic field lines in the interstellar medium tend to drape around expanding bubbles and to be compressed in shells while remaining more gently curved in the interiors. Although these fields are not yet mapped in full detail in the region of Geminga, models of the local interstellar medium suggest that the combination of bubbles and shells produces a complex field geometry. This geometry matters because it helps guide charged particles such as high-energy electrons and positrons as they move through the region around the neutron star. Even without considering any specific emission processes, the presence of curved neutral hydrogen shells and hot low-density interiors shows that Geminga does not move through an untouched medium. It travels instead within a layered environment whose structure records the cumulative effect of many past stellar explosions, including the event that created the neutron star itself and likely several other supernovae in the same broader region of the local spiral arm. Geminga is not fixed on the sky. Over years and decades, careful measurements show that its position shifts steadily against the background of more distant stars and galaxies, revealing a high proper motion that marks it as a relatively nearby object, moving with significant speed through space. Proper motion is the apparent angular change in position of a source on the sky as seen from the Sun, and when combined with an estimate of distance, it gives a transverse velocity, the component of the star's motion that is sideways from the observer's point of view. For Geminga, this transverse speed is hundreds of kilometers per second, a value much larger than the motions of most ordinary stars in the local neighborhood. This high space velocity is a common feature of neutron stars, which often receive a strong kick during the supernova explosion that forms them. When the core of a massive star collapses, slight asymmetries in the explosion can push the newly formed neutron star in one direction, adding a substantial velocity to the motion it inherited from the original star's orbit in the galaxy. As a result, the remnant does not simply continue along the same path as its progenitor, but follows a new course tilted and offset relative to the surrounding population. Observations of Geminga over many years trace such a path. In high resolution, images its position relative to background sources shifts measurably, and by fitting a straight line to this motion, astronomers derive both the speed and the direction of its travel across the sky. Combined with distance estimates from parallax and other methods, these measurements indicate that Geminga moves through the local interstellar medium with a velocity that is supersonic with respect to the sound speed in the surrounding gas. Supersonic here means that the neutron star's speed exceeds the speed at which pressure waves travel in the thin, warm medium around it, an important fact for understanding how its motion interacts with the gas. The direction of Geminga's motion on the sky can be projected back in time to estimate where it was located in the past. When this track is followed backward for several 100,000 years, it leads to a region in the local spiral arm that may have hosted the massive star whose death produced the neutron star. This reconstruction is necessarily approximate because uncertainties in the distance, the true three-dimensional velocity and the age all combine to broaden the possible origin region. Nonetheless, the backward projection suggests that Geminga likely came from a part of the local arm, where previous generations of massive stars formed and exploded, contributing to the cavities and shells now seen in neutral gas. The current space motion of Geminga is a vector sum of three contributions. One is the orbital motion of the local arm around the center of the Milky Way, which it shares with the Sun and many nearby stars. Another is the peculiar motion of the progenitor star relative to the local standard of rest before it exploded. The third is the supernova kick imparted at birth. The first component is large but common to many objects, while the second and third distinguish the neutron star's path from that of its neighbours. Because the kick can be in almost any direction, the resulting velocity can tilt the path of the neutron star above or below the galactic plane, or cause it to move more radially inward or outward in the disk. In Geminga's case, the measured proper motion indicates a significant component of motion across the line of sight, combined with some vertical and radial movement inferred from models of the local gravitational field. These motions carry the neutron star gradually away from the region of its birth across a background of more distant stars that appear stationary on short timescales. For observers using high-energy telescopes, the slow drift of Geminga across the sky is important to track because precise positions are needed to accumulate data over many years and to associate gamma-ray and X-ray emission with the same compact source. As the neutron star shifts, analysis methods must account for its changing coordinates. Otherwise, the signal could be blurred or misassigned when combining observations taken at different epochs. The high proper motion also confirms that the source is galactic and nearby rather than an extragalactic object, since distant galaxies and quasars have negligible apparent motion in such time spans. Together with distance estimates and spectral measurements, the motion therefore helps secure Geminga's identity as a neutron star rather than another high-energy source class. Over timescales of hundreds of thousands to millions of years, a velocity of this size will displace Geminga by many hundreds of light-years, carrying it through regions of slightly different gas density and through different parts of the galactic gravitational field. As it moves above and below the midplane, the pull of the combined mass of stars and gas tends to bend its path back toward the plane, so that the neutron star follows a gently oscillating track rather than a straight line in the vertical direction. The velocity of Geminga through the interstellar medium also sets up conditions for the formation of shock structures in the gas. Any continuous outflow from the neutron star made of relativistic particles and magnetic fields meets the oncoming interstellar material as the star advances. Because the neutron star is moving faster than sound waves can propagate, in that medium the gas cannot adjust smoothly ahead of it. Instead, it forms a compressed region or bow wave in front of the star and a wake behind it where shocked and swept up material is carried downstream. While the detailed shapes of these structures and their high energy emission belong to later parts of the analysis, the essential point here is that Geminga's high proper motion ensures that it cannot be treated as a stationary source embedded in a static medium. It is a fast-moving remnant cutting through a structured low-density environment, its path and speed recorded in the gradual change of its position on the sky and in the dynamical state of the gas that it encounters along its way. Far from the compact body of Geminga, high-energy observations reveal that its influence extends over a region much larger than any ordinary star. In maps of gamma rays sensitive to very energetic photons, the emission near Geminga does not shrink to a point. Instead, it spreads over an angular size of several degrees on the sky, corresponding to a physical radius of tens of parsecs around the neutron star. This extended glow is interpreted as a halo of energetic electrons and positrons that have escaped from the immediate surroundings of the pulsar and now diffuse through the low-density interstellar medium described earlier. In this picture, the neutron star injects electrons and positrons with very high energies into the space around it over hundreds of thousands of years. After leaving the vicinity of the star, these particles wander outward through the local magnetic fields, scattering and changing direction many times. As they travel, they interact with background photons from the cosmic microwave background, from diffuse starlight, and from infrared radiation emitted by dust. In each interaction, an energetic electron or positron can transfer part of its energy to a low-energy photon, boosting that photon into the gamma-ray range in a process known as inverse Compton scattering. The result is a faint but spatially extended gamma-ray halo, centered on Geminga but spreading far beyond the scale of the neutron star itself. Observationally, this halo appears as a broad region where the gamma-ray brightness is enhanced above the surrounding background, with a surface brightness that gradually declines with distance from the central pulsar. The exact shape and intensity profile depend on how quickly the electrons and positrons diffuse, how long they have been injected, and how they lose energy as they move. By comparing measured gamma-ray maps with theoretical models of particle diffusion and radiation, astronomers infer properties of the transport of charged particles in the region around Geminga. One of the striking conclusions from these studies is that the effective diffusion of electrons and positrons in the inner part of the halo seems to be slower than in typical models of the broader galactic interstellar medium. In practical terms, this means that high-energy particles remain concentrated near Geminga for longer times than they would if they moved with the average diffusion rate assumed for the galaxy as a whole. A slower diffusion coefficient allows the halo to remain bright and compact in gamma rays, even though the neutron star is middle-aged and has been injecting particles for several 100,000 years. Outside, a certain radius diffusion appears to become faster and more consistent with the standard values, so that the halo can be described as a slow diffusion region embedded in a more rapidly diffusing background. The physical reasons for this slow diffusion may include turbulence in the magnetic field generated by the escaping particles themselves, or conditions left over from the original supernova remnant. Whatever the detailed cause, the net effect is that the region around Geminga acts as a kind of reservoir for energetic electrons and positrons, confining them on scales of tens of parsecs before they are able to leak into the wider interstellar medium. The size of the halo and the amount of gamma-ray emission it produces have important implications for the population of cosmic ray positrons measured near Earth. Several experiments detect an excess of high-energy positrons compared with simple expectations from interactions of cosmic rays with interstellar gas. Nearby pulsars like Geminga are natural candidates to supply such particles because they continuously inject electrons and positrons into space. However, if diffusion in the halo is as slow as some observations indicate, many of these particles may remain trapped near the pulsar for long periods and may not contribute strongly to the flux measured at the position of the Sun. Alternative models propose that the slow diffusion zone around Geminga is finite in size, and that beyond its boundary particles escape into a region of faster diffusion and can reach Earth in significant numbers. The current data do not yet fix all the relevant parameters, so the exact contribution of Geminga to the local positron excess remains under active study. Nevertheless, the existence of the halo itself is well established. Gamma-ray observations at very high energies detect extended emission around Geminga that cannot be explained by a point-like source alone, and the spectral shape of this emission is consistent with inverse Compton scattering by electrons and positrons of pulsar origin. At somewhat lower gamma-ray energies, the contrast between the halo and the broader galactic background is weaker, making the extended glow harder to detect, but constraints from these observations still provide valuable limits on the number and distribution of particles in the halo. As a result, a combined view from different instruments and energy ranges builds a more complete picture of how the halo behaves. Estimates of the halo radius from these studies fall in a range of several tens of parsecs, with a gradual transition from the inner slow diffusion zone to the outer region, in which particles mix more readily with the general cosmic ray population. Within this volume, the density of injected electrons and positrons is significantly higher than the average in the surrounding medium, and their interactions with background light and magnetic fields dominate the gamma-ray emission. The halo therefore serves as a direct probe of how charged particles propagate in a real galactic environment under conditions set by both the neutron star and the surrounding interstellar medium. Because Geminga is relatively nearby, the angular extent of its halo is large enough to be mapped in detail, making it a key laboratory for studying the microphysics of diffusion and energy loss. The presence of this extended halo shows that the influence of a neutron star is not confined to its immediate surroundings, but can shape the high-energy radiation and particle population over volumes that, while small compared with the entire galaxy, are large on the scale of the local interstellar medium. The extended glow around Geminga is sustained by a population of electrons and positrons that carry very high energies and move through the surrounding interstellar medium under the combined influence of magnetic fields, scattering and energy losses. These particles are created in and near the neutron star and then escape into the space around it, where they no longer remain tied to the compact object, but instead fill a region that extends for many tens of parsecs. Electrons and positrons are light-charged particles, and at the energies relevant here they travel at speeds close to that of light. Their motion is not a straight line because magnetic fields in the interstellar medium bend their paths, causing them to follow curved trajectories around field lines, and to be deflected by irregularities. On large scales, this motion can be described as diffusion, a gradual spreading outward from the source that depends on how tangled and turbulent the magnetic field is. The diffusion coefficient is a quantity that summarizes how fast this spreading occurs. In standard models of the galactic interstellar medium, this coefficient has a value that allows charged particles to travel long distances over the lifetimes of cosmic rays, smoothing out their distribution over large volumes. Observations of the halo around Geminga, however, suggest that near the neutron star the effective diffusion is slower than these average values. The electrons and positrons responsible for the halo also lose energy as they move. Two main processes dominate these losses at very high energies. One is inverse Compton scattering, in which an energetic electron or positron collides with a low-energy photon from the cosmic microwave background, from diffuse starlight or from infrared radiation, produced by dust and transfers part of its energy to that photon. The other is synchrotron radiation, in which a charged particle spirals around magnetic field lines and emits radiation most strongly at radio to X-ray wavelengths, depending on the energy of the particle and the strength of the field. Both processes gradually drain energy from the particles, with higher energy particles losing energy more quickly than lower energy ones. The balance between diffusion and energy loss sets the size and brightness profile of the halo. If diffusion were very rapid, electrons and positrons would move far from the neutron star before losing much energy, and the halo would be larger and fainter per unit area. If diffusion were very slow, particles would remain closer to the source, and the halo would be more compact and brighter. Because Geminga is middle-aged with an estimated age of several 100,000 years, the electrons and positrons in its halo have had a long time to diffuse and to cool. Models that follow their evolution therefore need to account for the continuous injection of new particles. Over this time, the energy-dependent losses and the spatially varying diffusion, very high-energy gamma-ray observations show that around Geminga, the surface brightness of the halo declines with distance from the neutron star in a way that favors relatively slow diffusion in the inner region. Inferred diffusion coefficients within tens of parsecs are smaller than the standard galactic average by 1 to 2 orders of magnitude. Beyond that scale, diffusion is thought to approach more typical values, so the environment can be described as a slow diffusion zone embedded in a larger region where particles move more freely. The physical cause of this slow diffusion is still under study. One possibility is that the streaming of energetic electrons and positrons away from the neutron star generates turbulence in the magnetic field, which then scatters subsequent particles more strongly and reduces their net transport speed. Another is that the local interstellar medium retains turbulence and irregular magnetic structures from the original supernova remnant and from other past explosions, leading to a region where charged particles are more effectively trapped. Distinguishing between these possibilities requires detailed comparison between observations and numerical models, and at present the data support the existence of slow diffusion, but do not uniquely determine its origin. The energy spectrum of the halo provides additional constraints. By measuring the gamma-ray flux at different energies, instruments can infer how many electrons and positrons exist at corresponding energies and how they are distributed in space. At the highest gamma-ray energies, where only the most energetic particles contribute, the halo is relatively compact because such particles lose energy quickly and cannot travel far before cooling. At lower gamma-ray energies, lower energy electrons and positrons contribute, and these can diffuse further before losing energy, so the halo appears more extended. This pattern, in which the apparent size of the halo changes with energy, is a natural outcome of diffusion with energy losses and can be used to refine models of the transport. In addition to inverse Compton emission, the same electrons and positrons produce synchrotron radiation in radio and X-ray bands. For Geminga, the detection of extended synchrotron emission from the halo is more challenging because of sensitivity limits and confusion with other sources, but upper limits and tentative detections help set bounds on the magnetic field strength in the region and on the total number of particles. Together with the gamma-ray data, these constraints suggest that the magnetic field in the halo is of the same general order as typical interstellar values, not dramatically stronger, and that the slow diffusion is more likely a result of turbulence and scattering rather than simply an unusually high field strength. The interplay between injection history diffusion and energy loss also means that the halo records the past activity of Geminga. Electrons and positrons injected long ago have by now cooled to lower energies and occupy larger radii, while more recently injected higher energy particles dominate closer to the neutron star. This layered structure in energy and radius is not directly visible in a single observation, but can be inferred by comparing models with multi-energy gamma-ray maps. In effect, the halo serves as a fossil record of the pulsar's spin-down power over time filtered through the processes that govern particle transport. Although the injection of electrons and positrons is tied to the detailed physics of the pulsar and its wind, the behavior of the halo at large radii depends mainly on the properties of the interstellar medium. This separation allows studies of Geminga to use the halo as a probe of diffusion and energy loss in the local environment, without requiring complete knowledge of the inner magnetospheric processes. By adjusting the diffusion coefficient to the energy dependence of the diffusion and the background radiation fields within reasonable ranges, models aim to reproduce the observed brightness and extent of the halo. The success and limits of these models provide insight into how representative the conditions around Geminga are for the broader galaxy, and how much variation exists from one region to another in the transport of high-energy electrons and positrons. Very high-energy observations refine the picture of Geminga's extended emission by focusing on the most energetic gamma rays, which probe the upper end of the electron and positron population around the neutron star. Ground-based observatories that detect gamma rays indirectly by recording the particle cascades produced when these photons strike the upper atmosphere have mapped a broad diffuse source of very high-energy gamma rays centered near the position of Geminga. This source is larger than the point spread function of the instruments and cannot be explained by a compact object alone. Instead, it is interpreted as the bright inner part of a very high-energy halo, where electrons and positrons with energies of many tera electron volts interact with ambient photon fields and produce gamma rays through inverse Compton scattering. These observations complement the space-based measurements at lower gamma-ray energies, providing access to the regime where energy losses are strongest and where only the highest energy particles contribute. The detection of this extended very high energy emission confirms that Geminga efficiently accelerates and releases electrons and positrons over long timescales, and that a significant fraction of these particles remain within a limited distance of the neutron star before cooling. The angular size of the very high energy halo, together with the estimated distance to Geminga, implies a physical radius of order tens of parsecs. Within this volume, the density of very energetic electrons and positrons is much higher than in the average interstellar medium. The brightness profile of the halo, which shows how the gamma-ray intensity declines, with distance from the pulsar, provides direct constraints on how fast particles diffuse and how quickly they lose energy. By fitting this profile with models that include diffusion and inverse Compton scattering, astronomers derive diffusion coefficients that are significantly smaller than the standard values usually adopted for the galactic cosmic ray population. This slow diffusion in the immediate surroundings of Geminga is a key result of the very high energy observations and has direct implications for the role of the neutron star as a source of cosmic ray positrons near Earth. Cosmic rays are high energy particles, mostly protons and heavier nuclei, but also electrons and positrons that travel through the galaxy and are detected when they reach the vicinity of the solar system. Measurements over the past decades have shown that the fraction of positrons in the local cosmic ray population at high energies is larger than predicted by simple models, in which positrons are produced only as secondary particles when primary cosmic rays collide with interstellar gas. This so-called positron excess suggests the presence of additional primary sources of high energy. Positrons and nearby pulsars are natural candidates, because they are known to produce electron-positron pairs and to inject them into the interstellar medium. Before the very high-energy halo measurements models that use standard diffusion coefficients and the known properties of Geminga suggested that it could be a major contributor to the local positron excess, given its proximity and age. In such models, electrons and positrons born near the neutron star diffuse outward relatively rapidly and fill a large region that includes the solar system. The number of particles arriving near Earth then depends on the total energy injected into pairs over the lifetime of the pulsar and on the distance between Geminga and the Sun. However, when the slow diffusion implied by the very high energy halo is taken into account, the situation becomes more complex. If diffusion is strongly suppressed over tens of parsecs around the neutron star, high energy electrons and positrons remain trapped near Geminga for a long time and lose much of their energy before they can escape into the broader interstellar medium. In that case, the contribution of Geminga to the positron flux at Earth would be smaller than earlier estimates because fewer high-energy particles would travel the several hundred light-years to the solar system. Detailed calculations that use the diffusion coefficients inferred from the halo observations indicate that under some assumptions, Geminga alone cannot account for the full positron excess measured near Earth, although it may still provide a non-negligible fraction. One way to reconcile a substantial contribution from Geminga with slow diffusion near the source is to assume that the region of suppressed diffusion has a finite size. Within this inner zone, particles move slowly and build up a dense population that produces the observed very high-energy gamma-ray halo. Beyond a certain radius, diffusion returns to values closer to the galactic average, allowing particles that succeed in reaching this boundary to propagate more efficiently toward the solar system. The number of positrons that eventually arrive near Earth then depends on the size of the slow diffusion zone, the transition to faster diffusion, the detailed injection history and the energy dependence of all these processes. Because each of these parameters carries uncertainties, models can yield a range of possible contributions, from Geminga from modest to more significant fractions of the observed positron excess. Current data favor scenarios in which Geminga is one of several nearby pulsars that together influence the local high-energy positron population, rather than a single dominant source, but the exact balance remains an open question. The very high-energy halo around Geminga is therefore not only a feature of this particular neutron star, but also an anchor point for broader studies of cosmic ray propagation. By comparing the halo properties of Geminga with those of other pulsars that show extended very high-energy emission, researchers investigate whether slow diffusion zones are a common feature around pulsars, or whether Geminga occupies a special environment. If slow diffusion is widespread near many pulsars, then the general picture of how cosmic rays move through the galaxy may need to incorporate a patchwork of regions with different transport properties rather than a single uniform diffusion coefficient. This would influence not only the interpretation of the positron excess, but also the modelling of gamma-ray emission from the galactic plane and the expected signatures of other nearby sources. Another aspect of the very high-energy halo concerns its energy spectrum. Measurements show how the gamma-ray flux from the halo changes with photon energy, and these data can be translated into an underlying spectrum of electrons and positrons. By comparing this inferred spectrum with models of pair production in the pulsar magnetosphere, and in its immediate surroundings, astronomers can estimate how much of the spin-down power of Geminga, the energy lost as it gradually slows its rotation, is converted into high-energy pairs. For Geminga, the efficiency appears to be substantial, supporting the idea that middle-age pulsars can act as powerful accelerators of electrons and positrons over long periods. At the same time, the shape of the spectrum, including any cutoffs or breaks at high energies, provides information about the maximum energies reached, and about any changes in the injection process over time. Together, the spatial profile and energy spectrum of the very high-energy halo form a consistent, though still incomplete picture. Geminga is a nearby neutron star that has filled its surroundings with a population of very energetic electrons and positrons. These particles diffuse outward through a region where transport is slower than average, interact with background photons to produce extended gamma-ray emission, and eventually leak into the wider galaxy. The resulting halo is bright enough and large enough to be studied in detail, making Geminga an important reference object for understanding how pulsars contribute to the high-energy particle and radiation environment of the local Milky Way. On scales smaller than the extended halo, the high-energy environment around Geminga becomes dominated not by slowly diffusing particles, but by a more directed outflow known as a pulsar wind, and the region where this wind is confined and made visible is called a pulsar wind nebula. A pulsar wind nebula is a cloud of relativistic particles and magnetic fields powered by a rotating neutron star. The neutron star loses rotational energy over time, and part of that energy leaves the star as a wind of electrons, positrons, and electromagnetic fields moving outward at speeds close to that of light. Close to the star, this wind is highly ordered, and flows almost freely because the density of surrounding gas is too low to slow it down. At some distance, however, the pressure of the wind balances the pressure of the interstellar medium and any material already present around the star. At this point, a termination shock forms where the wind is abruptly decelerated and compressed. Beyond the shock, the energy carried by the wind is partly converted into random motion of particles and into radiation. The volume filled by this shocked wind, threaded by magnetic fields and populated by high-energy electrons and positrons, is the compact nebula that surrounds Geminga on parsec and subparsec scales. In contrast to the halo, which shines mainly through inverse Compton scattering at gamma-ray energies and extends over tens of parsecs, the inner nebula produces synchrotron radiation that is brightest at X-ray energies and is confined to a region of order a fraction of a parsec around the neutron star. High-resolution X-ray observations reveal this nebula as an elongated structured source centered on Geminga, brighter and more sharply defined than the diffuse halo seen at very high energies. The difference reflects both the younger age of the particles in the nebula and the stronger magnetic fields and higher energy densities present there. In the inner nebula, electrons and positrons have only recently crossed the termination shock, so they still retain a large fraction of the energy they acquired from the wind. As they spiral around magnetic field lines, they emit synchrotron radiation that can reach into the X-ray band, with the most energetic particles producing the highest energy photons. Because synchrotron losses are strong at these energies, the brightest X-ray emission comes from regions relatively close to the neutron star where the particles have not yet had time to cool significantly. Farther out, the electrons and positrons radiate at lower energies, and the nebula fades away into the broader halo. In models of Geminga's pulsar wind nebula, the termination shock lies at a distance where the ram pressure of the wind balances the combined thermal and ram pressure of the surrounding interstellar medium. The exact radius depends on the power of the wind, the density of the ambient gas, and the velocity of the neutron star through that gas. Geminga is not as energetic as the youngest, most powerful pulsars in the galaxy, so its nebula is smaller and fainter than those associated with objects like the Crab pulsar. However, the surrounding gas density is low, and the neutron star moves at a high speed, so the shape of the nebula is not spherical. Instead, the wind is more strongly confined in the direction of motion and more freely extended downstream, producing an overall morphology that's elongated along the path of the star. X-ray images show a compact region close to Geminga and fainter emissions stretching away, indicating that the shocked wind is being swept back by the oncoming interstellar medium as the neutron star advances. Within this compact nebula, the flow of particles is complex. At the termination shock, the wind slows from highly relativistic bulk speeds to a sub-relativistic flow, and the magnetic field is compressed and reoriented. Downstream of the shock, the plasma moves away, carrying energy outward while it radiates. The flow can be anisotropic, stronger along certain directions, and it can be affected by the spin axis and magnetic axis of the neutron star, and by the orientation of the ambient magnetic field. These factors shape the brightness and extent of the nebula along different directions on the sky. For Geminga, detailed imaging reveals a structure that can be described in terms of a bright central region, short extensions and longer tails, all aligned in a way that reflects the star's motion and the surrounding medium. The synchrotron spectrum of the nebula, inferred from X-ray and radio measurements, shows that the particle population within it follows a power law in energy, with more low-energy particles than high-energy ones, as is common in shock-accelerated plasmas. The highest energy electrons and positrons radiate away their energy quickly and are confined to the immediate vicinity of the neutron star, while lower energy particles can travel further before cooling and can populate the extended parts of the nebula and eventually the halo. In this sense, the compact nebula serves as an intermediate region between the magnetospheric zone, very near the neutron star, and the large-scale halo in which particles move mainly by diffusion. It is the volume where energy leaves the ordered wind and becomes part of the disordered radiating plasma that fills the space around Geminga. Because Geminga is middle-aged, its pulsar wind nebula is relatively compact and modest in luminosity, compared with very young nebulae, which can be bright and extended in multiple bands. Nonetheless, the presence of a clear X-ray nebula around it is important. It confirms that even at this age, the neutron star continues to channel a significant portion of its spin-down power into a particle wind, and that this wind still interacts strongly with the interstellar medium. It also provides a direct view of the particle acceleration region, where electrons and positrons gain energies high enough to produce the observed synchrotron, and later inverse Compton emission. By comparing the size, brightness and spectrum of the nebula with theoretical models of pulsar winds and shocks, astronomers can estimate the fraction of the neutron star's rotational energy that is converted into relativistic particles, the magnetic field strength in the shocked region, and the characteristic energies of the accelerated particles. These estimates then feed back into the interpretation of the extended halo, since the same overall energy budget must account for both the compact nebula and the large-scale emission. The compact nebula also encodes information about the surrounding interstellar medium because its shape and scale are sensitive to the external pressure and to the relative motion between the neutron star and the gas. A higher ambient pressure or slower motion would produce a more symmetric nebula, while a lower pressure and faster motion favour an elongated structure with a compressed leading edge and a broad wake. For Geminga, the observed elongation is consistent with a neutron star moving supersonically through a low-density medium and with a wind that is confined and swept back by the oncoming gas. In summary, within this layer, the transition from the diffuse halo to the compact nebula marks a change from a regime where particles move mainly by diffusion through the interstellar medium to one where they are driven by a directed wind and shaped by a termination shock, and by the immediate balance of pressures around the neutron star setting. The stage for the detailed shock and tail structures seen in X-rays. As Geminga moves through the interstellar medium with a velocity that is faster than the speed of sound in the surrounding gas, its pulsar wind does not expand symmetrically in all directions. The neutron star carries its wind into oncoming material, and because the gas cannot respond quickly enough to the advancing object, a bow-shaped region of compressed and heated gas and shocked wind forms ahead of it. In fluid terms, this is a bow shock similar in principle to the shock that forms around any object that moves supersonically through a medium, but here the conditions are those of a very thin gas-strong magnetic fields and a relativistic outflow. The bow shock marks the boundary, where the pressure of the wind balances the ram pressure of the interstellar medium that flows past the neutron star in its own rest frame. Inside this boundary the pulsar wind dominates, outside it the ambient gas does. Because Geminga's motion is primarily in one direction, the bow shock is closer to the star on the upstream side, and more extended downstream, giving the overall structure a compressed head and a trailing wake. High-resolution X-ray images of Geminga reveal signatures of this bow shock and the associated nebula. Rather than a simple symmetric shell, the emission shows arcs, short bars, and elongated tails that together trace the interaction between the wind and the oncoming gas. Close to the neutron star, there is a compact bright region where the termination shock and the inner part of the nebula lie. Slightly farther out in the direction of motion, faint arc-like features appear interpreted as parts of the bow shock where shocked gas and particles radiate in X-rays. Downstream opposite to the direction of motion, one or more tails extend for distances of a fraction of a parsec, indicating the path along which shocked wind material is carried away. These tails have narrow widths compared with their lengths, and appear aligned roughly with the neutron star's velocity vector, although their detailed orientation can differ slightly as conditions change. The existence of several distinct components such as a central axial tail and lateral tails, or wings, suggests that the flow in the nebula is not uniform. It may be shaped by anisotropy in the pulsar wind by the geometry of the magnetic field, and by variations in the density of the interstellar medium. In some observations, the brightness and shape of these structures vary over timescales of a few years, showing that the interaction region is dynamic rather than static. Changes in the wind power, small fluctuations in the external medium, or instabilities in the shocked plasma can all contribute to this variability, shifting the apparent length of the tails, or altering the brightness of knots and arcs. The scale of the bow shock around Geminga is set by the balance of pressures. The stronger the wind power, and the lower the external density, the larger the standoff distance between the neutron star and the apex of the bow shock. Conversely, a higher ambient density, a weaker wind, or a higher relative velocity will pull the bow shock closer in. For Geminga, estimates of the standoff distance from X-ray morphology, combined with its known spin-down power and space velocity, indicate that it is moving through gas of relatively low density, consistent with the picture of a local bubble and surrounding cavities in the interstellar medium. The bow shock thus acts as a local probe of the medium immediately ahead of the neutron star, complementing the larger scale information derived from radio and soft X-ray maps of neutral and hot gas. The shape of the bow shock is also influenced by the direction and strength of the magnetic field in the surrounding space. Magnetic field lines can guide the flow of shocked particles, making it easier for them to move along some directions than others. If the external field is inclined with respect to the neutron star's velocity, the shocked region can become asymmetric, with one side of the tail brighter or more extended than the other. In Geminga, the presence of multiple tails and asymmetric features hints at such an influence, although the exact field geometry is not directly measured. Numerical simulations of pulsar wind nebulae moving through magnetized media produce a variety of shapes, some of which resemble the observed structures around Geminga, when appropriate parameters are chosen for the wind, the field, and the gas density. By comparing the observations with these models, astronomers infer that the Mach number of Geminga's motion, that is, the ratio of its speed to the sound speed in the ambient gas, is significantly greater than 1. This confirms that the neutron star is deeply in the supersonic regime where a well-defined bow shock and elongated tails are natural outcomes. The shock compresses and heats not only the external gas, but also the pulsar wind plasma enhancing particle acceleration and synchrotron radiation in the region just behind the shock. As the shocked material flows into the tails, it continues to radiate, but the energy of the particles gradually decreases because of synchrotron losses and expansion, so the surface brightness fades with distance from the star. Observations at different X-ray energies show that the highest energy emission is more concentrated near the neutron star, while lower energy X-rays can be traced farther along the tails. This energy-dependent structure is expected if electrons and positrons with higher energies lose their energy more quickly than lower energy ones as they traverse the magnetized shocked region. The bow shock and tails around Geminga also provide an important link between small and large scales in its environment. On the one hand, they are close enough to the neutron star that their properties depend sensitively on the wind power, the orientation of the spin and magnetic axes in the local magnetic field. On the other hand, they extend far enough into the surrounding medium that they begin to merge with the outer regions where diffusion and inverse Compton scattering take over as the main processes governing the transport and radiation of particles. In this intermediate zone, the flow transitions from a more ordered directed motion in the tails to a more isotropic distribution in the halo. The bow shock thus both reflects the immediate response of the interstellar medium to a fast-moving neutron star and feeds the larger reservoir of energetic particles that populate the extended gamma ray and very high-energy halo around Geminga. Detailed X-ray observations of Geminga show that its pulsar wind nebula is not a single smooth cloud, but a set of distinct elongated structures that trace how the shocked wind and surrounding gas interact. High-resolution images reveal three main components: a central axial feature that begins very close to the neutron star and extends backward along the direction opposite to its motion, and two lateral structures on either side that curve away and trail behind. Together, these features outline a complex bow shock system, shaped by the pulsar wind, the supersonic motion of Geminga, and the properties of the local interstellar medium. The axial structure is a narrow, bright tail that starts at the pulsar position and stretches for tens of arc seconds on the sky, corresponding to a length of a small fraction of a parsec at Geminga's distance. Its width is only a few arc seconds, so it appears as a thin comet-like extension, trailing directly behind the neutron star. Within this axial tail, the X-ray brightness is not uniform. Instead, it shows one or more compact enhancements, sometimes described as blobs or knots, separated by regions of lower surface brightness. Spectral analysis indicates that the X-ray emission from the axial tail has a hard spectrum, meaning that high-energy photons are relatively abundant compared with lower-energy ones. This is consistent with synchrotron radiation from very energetic electrons and positrons that have recently passed through a shock and are now flowing away from the neutron star. The distance from the pulsar to the far end of the axial tail sets a limit on how far such particles can travel before losing most of their energy to synchrotron radiation in the local magnetic field. The lifetimes of electrons energetic enough to emit X-rays of the observed energies match the time required to advect them along the tail at reasonable flow speeds, so the length of the tail is consistent with standard synchrotron cooling in a magnetized, shocked pulsar wind. The lateral structures extend much farther on the sky, reaching angular sizes of a few arc minutes, and corresponding to physical lengths of a few tenths of a parsec. they appear as two bent patchy tails that lie roughly on either side of the pulsar's projected path, curving away from the direction of motion. Their emission is also hard and non-thermal, again indicative of synchrotron radiation from relativistic electrons and positrons. Notably, there is little or no diffuse X-ray emission detected between the two lateral tails, so they do not form a continuous filled cone of emission. Instead, they outline boundaries or separate channels of flow. Their surface brightness is uneven with brighter segments and fainter gaps along their length, suggesting that the flow and particle acceleration in these regions are not uniform. The morphology of the lateral tails and the axial tail together is unusual when compared with some other bow-shock pulsar wind nebulae. In many systems, the brightest emission forms a single continuous comet, like tail behind the pulsar gradually fading with distance. In Geminga, the presence of two distinct lateral tails plus a central axial feature invites different interpretations. One class of models treats the lateral tails as regions where the boundary between the shocked pulsar wind and the surrounding medium is seen in projection. In that picture, the wind fills a shell-like structure behind the bow shock, and the outer edges of this shell appear brighter because of limb brightening, while the interior appears fainter. The lateral tails would then correspond to these brightened limbs, and the absence of emission between them would reflect the lower surface brightness of the interior. Another class of models instead regards the lateral tails as bent polar outflows, jets originating from near the magnetic poles of the neutron star and deflected backward by the ram pressure of the interstellar medium. In that scenario, the axial tail could be a separate component, possibly a jet aligned with the spin axis or a collimated flow of shocked wind material. Current data allow several such interpretations, and different physical pictures can be constructed that reproduce the observed brightness and spectra of the components. Time variability provides additional constraints. Comparing X-ray images taken at different epochs shows that features in the axial tail, such as the bright blobs, can change in brightness and position over timescales of a few years. Some blobs appear to move along the tail while others fade or brighten without obvious motion. The lateral tails also show hints of changes in structure and surface brightness. This variability indicates that the flow in the pulsar wind nebula is dynamic. Instabilities in the shocked plasma, changes in the pulsar wind, or small-scale variations in the ambient medium can all alter the appearance of the tails. In magnetized relativistic plasmas, processes such as magnetic reconnection and shear instabilities are expected, and they can create transient structures like bright knots and fragmented arcs. Geminga's nebula therefore offers an opportunity to study such processes in a real system, under conditions that are quite different from those in laboratory plasmas. The overall energetics of the nebula are modest compared with the total spin-down power of the pulsar. The X-ray luminosity of the tails is a small fraction of the power Geminga loses as it slows its rotation, and it is lower than the luminosity of the pulsar's magnetospheric emission. This is typical of middle-age pulsars, where only part of the available energy is channeled into a visible wind nebula. The hard spectra of the lateral tails and axial tail with photon indices near 1 in simple power law fits show that the particle populations in these regions are dominated by high-energy electrons and positrons. The relatively low X-ray efficiency suggests that much of the energy released in the wind either goes into particles that radiate at other wavelengths, such as gamma rays via inverse Compton scattering, or is carried away without radiation as bulk, kinetic and magnetic energy. Observations at optical and ultraviolet wavelengths have searched for corresponding emission from the bow shock and tails, including possible narrow line emission from neutral hydrogen excited in the shock. For some bow shock pulsars, such emission appears as thin H-alpha arcs that trace the sharp edge of the shock front. In the case of Geminga, such optical emission is weak or absent, likely because the surrounding medium is hot and has a low fraction of neutral hydrogen, or because the density is simply too low to produce a bright optical shock. This absence is consistent with the picture of Geminga moving through a low-density, high-temperature phase of the local interstellar medium. The length of the tails combined with estimates of the flow speed in the shocked wind also acts as a clock for the interaction. If particles move along the tails at a significant fraction of the speed of light, the observed lengths correspond to flow times of a few years to a few decades. Over these times, synchrotron losses modify the energy distribution of the electrons and positrons, causing the spectrum to soften with increasing distance from the pulsar. While the current observations of Geminga's nebula are not always sensitive enough to trace subtle spectral gradients along the tails, marginal evidence for such trends reinforces the picture of particles being injected near the neutron star, advected downstream and cooling as they go. The combination of axial and lateral tails, their hard spectra, their variability and their alignment with the neutron star's proper motion make Geminga's pulsar wind nebula a benchmark example of a bow-shock nebula around a middle-aged pulsar. It anchors models of how a relativistic pulsar wind interacts with a low-density medium at high Mach number, and how the resulting structures fill the space between the compact magnetospheric region close to the neutron star and the much larger halo, where particles diffuse more freely into the surrounding interstellar medium. Closer to Geminga than the bow-shock and tails, the physical conditions become dominated by the neutron star's own magnetic field and rotation. This region, where the magnetic field and the plasma attached to it control the motion of charged particles, is called the magnetosphere. A magnetosphere around a neutron star is the space in which the star's magnetic field is strong enough to guide charged particles and force them to move along curved magnetic field lines rather than in straight paths. Geminga is a pulsar, meaning a rotating neutron star that emits beams of radiation that sweep through space as it spins. Its rotation period is about 1/4 of a second, so the star completes several rotations each second, and over hundreds of thousands of years it gradually loses rotational energy, a process called spin down. The energy lost in this way powers the magnetospheric radiation, the pulsar wind, and ultimately the extended nebula and halo. The magnetic field of Geminga is very strong by ordinary standards, many orders of magnitude stronger than the field at the surface of a typical planet. Field lines emerge from near one magnetic pole arc through space and return near the opposite pole, forming a pattern roughly similar to that of a bar magnet, but distorted by rapid rotation and by plasma effects. Close to the neutron star, many of these field lines are closed, meaning that both ends connect back to the star. Farther out, there are open field lines that extend outward and do not return directly to the surface. The boundary between these regions and the geometry of the open field line zone play a key role in how and where particles are accelerated and radiation is produced. The outer limit of the region that co-rotates with the star is defined by a notional surface called the light cylinder, an imaginary cylinder centered on the rotation axis, where the linear speed of co-rotation would equal the speed of light. Beyond this radius, matter cannot remain in rigid corrotation without exceeding the speed of light, so the structure of the field and plasma must change. The interplay between strong magnetic fields, rapid rotation, and a background of charges gives rise to electric fields that can accelerate particles to very high energies along certain paths in the magnetosphere. In Geminga's case, as in other pulsars, the magnetosphere is filled with electrons, positrons, and possibly ions that are continually created and destroyed. Near the neutron star surface, strong fields and intense radiation fields can produce pairs of electrons and positrons when high-energy photons encounter the magnetic field or other photons. These fresh charges then move along field lines and can trigger more pair production, forming a cascade that populates the magnetosphere with plasma. the accelerated charges emit radiation as they move along curved field lines, a process called curvature radiation, and as they interact with the magnetic and electric fields through other mechanisms. At different altitudes and locations in the magnetosphere, these processes can produce photons from radio frequencies up to gamma-ray energies. The precise location of the main emission zones depends on the structure of the magnetic and electric fields, which in turn depends on the inclination between the magnetic axis and the rotation axis, and on the distribution of charges. In some models, gamma rays are produced in regions near the outer magnetosphere, where field lines cross the light cylinder, or where gaps in the plasma distribution allow strong electric fields to accelerate particles. In others, significant emission can also occur at lower altitudes closer to the star. For Geminga, observations show that the pulsar is especially bright in gamma rays, with a pulse profile that repeats every rotation and exhibits characteristic peaks as the beams sweep past the observer. These pulses are a direct signature of the rotating magnetosphere as beams of high-energy radiation cross the line of sight. The fact that Geminga is bright in gamma rays but almost silent in ordinary radio observations can be understood in terms of beam geometry and emission efficiency at different wavelengths. Radio emission in pulsars is thought to originate closer to the neutron star surface along open field lines near the magnetic poles, in regions where coherent emission processes operate. The radio beam is relatively narrow and tied closely to the geometry of the polar cap region. Gamma-ray emission, by contrast, often arises higher in the magnetosphere, where field lines fan out and cover a larger solid angle. As a result, the gamma-ray beams can be broader and arranged in such a way that they intersect a larger range of viewing directions. If the Earth lies in a direction that intersects the gamma-ray beams but misses or only grazes the narrower radio beams, the pulsar will appear gamma-ray bright and radio quiet. Additionally, the intrinsic efficiency of radio emission may decrease as pulsars age and their magnetic and rotational parameters change, so that some middle-aged pulsars produce weaker radio signals that fall below the sensitivity of many surveys, even if a narrow radio beam would otherwise cross the line of sight. Geminga appears to be one such case. Searches for radio pulses from Geminga at various frequencies have found at most very faint or disputed signals, while gamma-ray observations show strong regular pulsations. In the framework of standard pulsar theory, this behavior does not imply that Geminga violates physical laws. Instead, it reflects how emission depends on geometry, frequency, and sensitivity. The magnetosphere of Geminga operates under the same basic principles as other rotation-powered neutron stars, converting rotational energy into electromagnetic radiation and into particle outflows, but the particular arrangement of its beams relative to the Earth, coupled with its age and field strength, leads to a spectrum dominated by gamma rays. The pattern of gamma-ray emission from Geminga carries information about the geometry of the magnetosphere. The number of peaks in the light curve their separation in phase, and how the spectrum changes across the pulse all depend on the inclination of the magnetic axis, the orientation of the rotation axis, and the location of the main emission zones. Models of outer magnetosphere emission, where particles are accelerated in gaps near the last open field lines, can reproduce many of the observed features. These models place the gamma-ray emission in regions that are several neutron star radii, away from the surface, often near or just inside the light cylinder. In such regions, the magnetic field is still strong but weaker than at the surface, and the curvature of field lines and the available potential drops are favourable for generating high-energy photons. The magnetospheric radiation is also connected to the pulsar wind. Beyond the light cylinder field lines open, and the plasma is carried outward in a flow that forms the wind. The amount of energy carried away in this wind depends on how the magnetosphere loads field lines with plasma and on the spin-down rate of the neutron star. Geminga's measured spin down indicates that it loses rotational energy at a rate sufficient to power both its magnetospheric gamma-ray emission and its wind nebula. The division of energy between these channels is an important parameter for models of the system, but in both cases the ultimate energy source is the same: the rotating magnetic field of the neutron star and the currents that flow within its magnetosphere. In gamma-ray observations, Geminga stands as one of the brightest persistent sources in the sky, its pulsed emission clearly revealing the signature of a rotation-powered neutron star. The magnetosphere is the engine that maintains this emission, structured by a strong magnetic field, rapid rotation, and a continuous supply of charges. Within this engine, particles are accelerated to high energies, radiate gamma rays in a beamed pattern tied to the star's rotation, and feed the particle populations that later appear in the compact nebula and the broader halo. The gamma-ray pulses from Geminga arise from the same magnetospheric structure described earlier, yet their prominence compared with the weakness of any detected radio signal gives this neutron star its reputation as a silent pulsar in radio surveys. As Geminga rotates once every roughly 1/4 of a second regions in its magnetosphere, where particles are strongly accelerated, sweep beams of high-energy radiation through space. When one of these beams crosses the line of sight to Earth instruments record a peak in the light curve. When it misses, the flux drops. Over each full rotation, this pattern repeats, producing regular gamma-ray pulses that mark the spin of the neutron star. Observations with space-based gamma-ray telescopes show that Geminga's light curve contains distinct peaks, separated in phase with intervals of lower emission between them. These peaks are interpreted as moments when the line of sight intersects different parts of the high-altitude emission zones in the magnetosphere, such as regions near the outer gaps or along the last open field lines near the light cylinder. The gamma-ray spectrum is non-thermal, extending up to energies of many billions of electron volts, and rolling over at higher energies in a way consistent with curvature radiation and related processes in strong magnetic and electric fields. The stability of the pulse profile over years confirms that the underlying magnetospheric structure is robust, even as the overall spin gradually slows. In contrast, repeated searches for radio pulses from Geminga have found no strong persistent signal at the frequencies commonly used in pulsar surveys. Some observations at low radio frequencies have reported tentative or marginal detections, while many others have yielded only upper limits on any pulsed radio flux. The overall picture is that if Geminga emits radio waves at all, the emission is either very faint, strongly confined to a narrow beam that does not cross the Earth, or both. This combination of bright gamma-ray pulses and an almost absent radio counterpart makes Geminga one of the archetypal radio-quiet gamma-ray pulsars. Before such objects were recognized, most known pulsars were discovered through their radio emission, and models of pulsars were guided by this sample. In those models, strong radio beams were assumed to be a defining observational signature, and gamma rays were often treated as a secondary or harder to detect component. The discovery of Geminga as a bright gamma-ray pulsar with no clear radio counterpart expanded this picture and showed that selection effects are important. Pulsars whose radio beams do not intersect the Earth, or whose radio emission has faded below survey sensitivities, can still be prominent at higher energies, where beams are broader or emission zones are located differently in the magnetosphere. The difference between Geminga's gamma-ray and radio behavior can be understood by considering how emission geometry and efficiency change with altitude and frequency. Radio emission is thought to originate at relatively low altitudes, above the magnetic poles along bundles of open field lines that form a cone-shaped beam. The half-opening angle of this beam depends on the location of the emission region and on the magnetic field geometry. For a given pulsar, only observers whose line of sight passes through this narrow cone, At some point in the rotation we'll detect strong radio pulses. Gamma-ray emission in many models is produced farther out in the magnetosphere, closer to the light cylinder, or in outer gaps. Field lines in these regions are more widely spread, and the resulting beams can form broad fan-like patterns that sweep across larger fractions of the sky. For Geminga modelling of the gamma-ray light curve suggests that the combination of magnetic inclination and viewing angle places the Earth in a region where the outer magnetospheric beams cross the line of sight, while the narrower radio beams from lower altitudes do not. In this configuration, the pulsar appears bright in gamma rays and quiet in radio, even if some radio emission is present along directions that are not sampled. Age and magnetic field strength also influence the radio output. As pulsars spin down and their magnetic fields evolve, conditions in the low-altitude regions that support coherent radio emission may change. In some middle-age pulsars, radio beams appear to shrink or weaken, and their emission can become intermittent or undetectable. Geminga belongs to this middle-age population, with a characteristic age of several 100,000 years, and a magnetic field strength that is strong but lower than that of the youngest, most energetic pulsars. It occupies a region of parameter space where radio efficiency may be reduced, and where the emission altitude may be such that the beam is relatively narrow. Gamma-ray emission, however, can remain efficient over a longer span of a pulsar's life, because the outer magnetosphere continues to accelerate particles as long as the star retains significant rotational energy. As a result, Geminga can maintain bright gamma-ray pulses, while any radio output is faint or highly directional. The path by which Geminga was identified illustrates how these emission properties interact with observational strategies. In high-energy surveys, the source first appeared as a bright, steady gamma-ray emitter, with no obvious counterpart at other wavelengths. Only after improved timing analysis and longer datasets were gamma-ray pulsations detected, revealing a neutron star with a spin period of a fraction of a second. Subsequent X-ray observations found a pulsating counterpart at the same period, consistent with heated regions on the neutron star surface, or with magnetospheric emission at lower energies. Radio telescopes, however, did not detect a comparable pulsed signal at most frequencies, even when pointed directly at the position of the gamma-ray source. Geminga was thus recognized as a pulsar primarily through its gamma rays and X-rays, not through radio, and it helped establish that gamma-ray timing alone can uncover rotation-powered neutron stars. This in turn led to the discovery of many more radio-faint or radio-quiet gamma-ray pulses in later surveys. The gamma-ray pulse profile of Geminga carries additional information about the magnetospheric geometry. The separation between peaks, the relative heights of the peaks, and the presence of interpeak emission can be matched to models in which the emission arises from specific regions, such as outer gaps or slot gaps, that extend along the last open field lines. By adjusting parameters such as the inclination angle between the magnetic and rotation axes and the viewing angle of the observer, these models reproduce the overall pulse shape. In many solutions, the radio beam, if present, is oriented such that it either narrowly misses the Earth or intersects the line of sight only at altitudes where emission is weak. In this way, modelling supports the idea that Geminga is not a fundamentally different kind of neutron star, but rather an example in which the high-energy beams happen to cross the Earth, while any coherent radio beam does not. The absence of strong radio pulses also shapes how the timing of Geminga is measured. Radio pulses are often timed with great precision using narrow radio pulses that allow measurements of rotation period and its derivatives over decades. For Geminga gamma-ray and X-ray pulses must serve this role. These pulses are broader and have lower photon counts, so the timing precision is lower than in the best radio cases, but it is still sufficient to track the gradual slowdown of the rotation and to search for phenomena such as glitches, small, sudden changes in spin. The long-term gamma-ray timing of Geminga has provided estimates of its spin-down rate from which parameters such as its characteristic age and inferred magnetic field strength can be derived through standard formulae. These parameters place Geminga comfortably among other middle-age pulsars in diagrams that plot spin period against period derivative, reinforcing the view that its radio quietness is an observational effect rather than a sign of an exotic engine. In the broader context of neutron star populations, Geminga is one member of a growing class of gamma-ray selected pulsars. These objects show that the population of rotation-powered neutron stars is larger and more diverse in its observable properties than implied by radio surveys alone. Some pulsars are bright in both radio and gamma rays, some are strong in radio but weak in gamma rays, and others, like Geminga, are strong in gamma rays but faint or undetected in radio. The differences arise from a combination of beam geometry emission physics at different wavelengths and the sensitivity and selection of observational instruments. Geminga's importance in this context lies in showing that a neutron star can be a prominent gamma-ray pulsar while appearing almost silent in radio, a situation that fits naturally within existing pulsar theory when geometry age and survey limits are taken into account. Beneath the magnetosphere and the pulsar wind, Geminga itself is a compact star with a solid outer surface and crust only about 10 kilometers across, yet containing more mass than the Sun. A neutron star surface is not a visible glowing photosphere like that of an ordinary star, but a thin, dense layer where matter changes from the solid crust to the overlying atmosphere. The gravity at this surface is extremely strong, many orders of magnitude higher than at the surface of a typical main sequence star. Under such gravity, any irregularities are flattened and any extended atmosphere is compressed into a very thin layer, only a few centimeters to a few meters deep, depending on composition and temperature. If a person could stand there, which current physics does not allow, the gravitational pull would be so intense that nothing could remain upright or intact. In practice, only dense matter bound by nuclear forces can support itself in this environment. The crust consists of atomic nuclei arranged in a lattice submerged in a sea of electrons. Near the surface, where densities are lower than deeper inside these nuclei, resemble very heavy versions of familiar elements, where most of the electrons have been stripped away by the pressure and temperature. As depth increases, pressure forces electrons into the nuclei, converting protons into neutrons and changing the composition toward neutron-rich nuclei. At some point, the density becomes so high that neutrons begin to drip out of the nuclei and form a continuous background, and the matter transitions into a region where nuclei and free neutrons coexist. The exact sequence of nuclei and the detailed structure of this transition depend on the equation of state of dense matter, which is still uncertain, but the broad picture of a solid crust composed of neutron-rich nuclei in a lattice is widely accepted. On and just below the surface, thermal and magnetic processes shape what telescopes detect in X-rays. Geminga emits X-rays that include both a thermal component attributed to hot regions on or near the surface and a non-thermal component from magnetospheric or nebular emission. The thermal component is often modelled with simple spectra resembling those of a hot dense surface or small hot spots, though these models are approximations because a neutron star atmosphere does not emit exactly like an idealized black body. For a middle-aged neutron star like Geminga, the global surface temperature is expected to be in the range of a few 100,000 to around 1 million. Kelvin having cooled from much higher temperatures in the first tens of thousands of years after formation. However, observations suggest that the entire surface may not radiate uniformly. Instead, some regions, likely near the magnetic poles, where charged particles from the magnetosphere return and deposit energy, can be hotter than the surroundings. These hotspots produce pulsating thermal X-ray emission as the star rotates because their visibility changes with rotation phase. In Geminga, X-ray timing reveals pulsations that align with the spin period known from gamma-ray observations. The shape of these X-ray pulses and how the spectrum changes with phase point to a combination of thermal emission from one or more hot regions and non-thermal emission from magnetospheric processes. By fitting phase-resolved spectra with models that include thermal components associated with small areas, and in some cases a cooler component from a broader surface region, astronomers infer approximate temperatures and sizes for the emitting zones. These fits are not unique because they depend on assumptions about the atmosphere composition, the magnetic field configuration at the surface, and the gravitational redshift which alters the observed spectrum compared with the emission in the local frame. Nonetheless, they provide broad constraints. The inferred radii for putative hotspots are much smaller than the full neutron star radius, consistent with emission from restricted polar caps, while the inferred temperatures are higher than the average temperature expected for the overall surface at this age. The global surface emission, if present, is cooler and harder to detect with current instruments, especially if non-thermal components and background noise compete in the same energy range. The strong surface gravity significantly affects the appearance of the neutron star. Light emitted from near the surface is bent by the gravitational field so that more than half of the stellar surface can be visible at once to a distant observer. This gravitational light bending smooths the observed pulse profiles from hotspots because regions that would otherwise rotate out of view can remain visible for longer portions of the spin cycle. When modelling Geminga's thermal pulse shape, this effect must be included along with the orientation of the rotation axis and the location of the hot regions. The degree of bending depends on the ratio of the neutron star's mass to its radius, so in principle, detailed modelling of surface emission can provide constraints on this ratio and hence on the equation of state. In practice, uncertainties in distance, atmosphere, composition and geometry limit how tightly these constraints can be drawn from current data. The composition of the outermost layers is another area where observations and theory meet. Shortly after formation, a neutron star may retain a thin layer of light elements such as hydrogen or helium on its surface, either from fallback material after the supernova or from accretion from the surrounding environment. Even a very small mass of such elements can form a fully covering atmosphere because the gravity compresses them into an extremely thin shell. If these light elements remain, they alter the emergent spectrum compared with a surface made of heavier elements, or bare nuclear matter, making it harder or softer at given energies. Over time, processes such as particle bombardment and diffusive nuclear burning can change the composition or remove light elements, leaving heavier nuclei at the surface. For Geminga, spectral fits have been attempted with both light element atmosphere models and simple blackbody or heavy element models, and while some combinations provide better agreement with the data, the uncertainties are still large enough that a unique composition has not been firmly established. It is clear, however, that whatever atmosphere exists is extremely thin compared with the neutron star radius, and that the underlying crust provides a rigid base. The surface also anchors the magnetic field. Field lines that extend into the magnetosphere and out into the pulsar wind are rooted in the crust, and any movement or evolution of the field over long time scales is tied to the electrical and thermal properties of the crustal material. Processes such as ohmic decay and the motion of magnetic flux tubes in the interior can gradually change the field strength and geometry, affecting both the spin down and the surface emission. For a middle-aged pulsar like Geminga, these changes are slow on human timescales, but they form part of the long-term evolution of the system. Surface cooling is another aspect of this evolution. Neutron stars cool primarily through neutrino emission from their interiors in the first tens of thousands of years, and then increasingly through photon emission from their surfaces as they age. By the time a neutron star reaches the age of Geminga, its interior has likely cooled substantially and the surface temperature has dropped to values where X-ray thermal emission is modest. Measurements of this emission combined with estimates of the age-placed Geminga on neutron star cooling curves, which are theoretical tracks that describe how temperature declines, with time for different interior compositions and processes. The position of Geminga on such curves is broadly consistent with standard cooling models, though the uncertainties in temperature and age are too large to distinguish among detailed microphysical scenarios. What can be said securely is that Geminga's surface has cooled from its initial post-supernova state, that it now radiates thermal X-rays primarily from limited regions that are heated by returning magnetospheric particles and residual internal heat, and that this radiation provides one of the few direct probes of conditions at and just beneath the crust in a middle-aged neutron star. Deep below the solid crust of Geminga matter reaches densities far beyond those found in ordinary atomic structures, and the familiar distinction between nuclei and electrons begins to blur. The outermost part of the interior beneath the crust is often called the outer core. In this region, the pressure is so high that most protons and electrons have combined into neutrons, leaving a fluid made primarily of neutrons with a smaller fraction of protons, electrons, and possibly muons. The neutrons are packed closely enough that their quantum mechanical properties become important on macroscopic scales. Many models predict that at these densities and temperatures neutrons form a superfluid, a phase in which they flow without internal friction, while the minority protons form a superconducting fluid that carries electric currents with little or no resistance. The presence of such superfluid and superconducting components influences how the neutron star cools, how it responds to stresses, and how its rotation changes over time. Deeper still, in what is called the inner core, the density may reach several times the density of atomic nuclei. Under these conditions, the behavior of matter is not fully known. One possibility is that it remains a fluid of neutrons, protons, and leptons with different pairing states and superfluid properties. Another is that additional particles such as hyperons containing strange quarks appear and share the pressure support. A further possibility is that nucleons dissolve into their constituent quarks, forming a phase of deconfined quark matter, perhaps in combination with hadronic matter. At present, observations do not decisively select among these options. Instead, they constrain the range of possible equations of state, which are relations between pressure density and temperature for the matter inside the star. The equation of state determines how compressible the material is, and in turn how the pressure rises with depth. For a given equation of state, there is a specific relationship between the mass and radius of a neutron star and a maximum mass beyond which the star cannot support itself against gravity. Measurements of neutron star masses, radii, and cooling behavior across many objects restrict which equations of state are viable, ruling out those that would produce stars too large, too small, too soft, or too stiff compared with what is observed. Geminga contributes to these constraints in a more limited way because its mass and radius are not yet measured precisely. Its spin period, spin down, rate estimated age, and surface emission patterns are broadly consistent with models in which neutron stars of about 1 to 2 times the mass of the Sun and radii of about 10 to 15 kilometers have interiors made of dense nuclear matter with superfluid components. These properties do not single out a unique internal composition, but they fit comfortably within the same general framework that describes other rotation-powered neutron stars. In theoretical models of the interior, the transition from the crust to the outer core occurs at a density of roughly half to about the density of atomic nuclei. Above this transition, the lattice of nuclei dissolves, and matter becomes a fluid. Neutrons and protons interact strongly through nuclear forces, and the balance between attractive and repulsive components of these forces, together with the requirements of quantum statistics, sets the pressure at each density. the presence of even a small fraction of protons and leptons is important because they carry charge and influence the star's ability to conduct electricity and support magnetic fields. Superfluidity and superconductivity in these components change how heat and angular momentum are transported. For example, a neutron superfluid can carry angular momentum in quantist vortices, which may pin to the crust and unpin in sudden events, potentially explaining glitches, small abrupt changes in rotation seen in some pulsars. While no large glitches have been firmly identified in Geminga so far, the same underlying physics is expected to apply. In the deeper inner core, if hyperons or deconfined quarks appear, they open new channels for neutrino emission and can change the stiffness of the equation of state, affecting both cooling and the maximum mass. However, models that include large amounts of such exotic components often predict stars that are too soft to reach the highest measured neutron star masses. This tension between possible inner core compositions and observed masses keeps the physics of the inner core an active research area. Geminga's age and temperature place it in a regime where the dominant cooling mechanism has likely transitioned from internal neutrino emission to photon emission from the surface, with residual neutrino processes still contributing at lower level. The cooling history up to this point would have depended on which neutrino processes were available in the core, which in turn depends on whether matter is purely nucleonic or includes more exotic phases. Standard cooling models with nucleonic matter and superfluidity can reproduce the approximate temperatures inferred for middle-aged neutron stars like Geminga, while more rapid cooling scenarios would predict lower surface temperatures than observed. Given the uncertainties in distant interstellar absorption and atmosphere models, Geminga's thermal emission does not yet strongly favour one detailed interior model over another, but it is consistent with a relatively standard nucleonic core with superfluid components. Another way in which the interior enters observable behaviour is through the star's response to the loss of rotational energy. As Geminga spins down under the torque of its magnetosphere, and when its rotation rate decreases and the centrifugal support against gravity diminishes slightly. The interior adjusts by contracting a small amount, and stresses can build up in the solid crust and in the superfluid interior. In some neutron stars, this adjustment proceeds smoothly. In others, accumulated stress is released in discrete events that produce glitches. The lack of large glitches in Geminga over the timescales observed suggests either that any such events are rare, or that the interior and crust relax more gradually. Both possibilities are compatible with standard models of superfluid neutron star interiors. The distribution of mass and pressure inside Geminga also influences its moment of inertia, which determines how much energy is stored in rotation for a given spin rate, and how quickly the star spins down for a given torque. When combined with measurements of the spin-down rate, the moment of inertia in principle can provide additional constraints on the equation of state. In practice, the torque exerted by the magnetosphere is not perfectly known, so individual objects like Geminga cannot yet yield precise interior constraints through this route. Instead, they contribute to statistical studies that consider many pulsars together. In all of these examples, the interior layers of Geminga are inferred rather than seen directly. No observation can probe the core in the same way that X-ray and gamma-ray telescopes probe the magnetosphere and nebula. Instead, theoretical models of dense matter guided by nuclear physics experiments on Earth, and by observations of many neutron stars, are used to describe the core, and the consistency of these models with Geminga's observable properties is checked. The result is a picture in which Geminga's interior is made of dense nuclear matter that likely includes superfluid neutrons and superconducting protons in the outer core, and possibly more exotic components in the inner core, all arranged in layers that support the crust and surface against collapse. Its global properties suggest that its equation of state is neither extremely soft nor extremely stiff, but lies within the range compatible with other neutron star measurements. Within that broad range, many microphysical possibilities remain open, so Geminga serves as one more data point in the ongoing effort to understand how matter behaves at densities far beyond those achievable in terrestrial laboratories, without yet pinpointing a single unique description for its core.